A very good morning and welcome to this course on the foundations of continuum mechanics. Today we will be talking about the topic on Mohr's circles. So let us get started. The topics for today's lecture are as follows. First, we'll introduce Mohr's circles to you, and I'll talk about the idea of a stress plane because we'll be drawing these circles on a plane called the stress plane. Then I'll talk about the feasible stress space and the derivation of Mohr circles. We'll go through some mathematical work to derive the equations of these circles and then find out the feasible stress space from the inequalities. Thirdly, we will talk about how to find stress maxima using the Mohr circles. In fact, that is the aim of this discussion, that we have to identify the maximum and minimum values for normal and shear stresses using these circles. Then we'll talk about a correspondence between this stress plane where the Mohr's circles are drawn, where the feasible stress space exists, and the physical space, which is our 3D right-handed Cartesian coordinate system OX1, x2, x3. Lastly, I'll talk about the fact that Mohr circles are not just useful for identifying the stress maxima, they can also be used to find the sigma n, sigma s pairs, that is, a point on the stress plane for a given normal vector n hat in the physical plane. So let's get started with an introduction to Mohr's circles. So in the previous lecture, we talked about writing the state of stress in a slightly modified way. So we tabulate all the n hats which correspond to the cutting plane as shown in the figure passing through the point P. And instead of writing the stress vectors or the traction vectors, instead we write a collection of sigma n, sigma s pairs. Because the traction vector can be split into its normal and shear components as sigma n, sigma s. So if we know the components and the n hat, we can find the traction vector uniquely. So now that we have the state of stress given in this form of n hats and the pair of sigma n, sigma s points, instead of finding the maximum value for the traction vector, we instead are interested to find the maximum and minimum values of sigma n and sigma s. This is because it is more useful to find the conditions where the normal stress becomes the maximum or the shear stress becomes the maximum, rather than simply finding the situation where the traction vector becomes the maximum. So in the last lecture, we had discussed about the Lagrange multiplier method, which is an analytical technique to find the stress maxima values. And today we'll be talking about an analysis method, which is called the method of Mohr's circles. And this method of Mohr's circles helps us look at the situation geometrically and visualize the maxima state of stress more comfortably and easily. So let us now get into discussing the Mohr's circles in the stress plane. So here is our stress plane where we have sigma n on the x-axis and sigma s on the y-axis. So please remember that physically speaking, if we have an n hat corresponding to a cutting plane passing through a point P, then we'll have a corresponding sigma n, sigma s pair. So every n hat corresponding to a cutting plane through the point P will correspond to a point on this stress plane. And if I take the locus of all those points, sigma n, sigma s, corresponding to all the n hat values passing through the point P, we get a region. And this region is called the feasible stress space. So the aim in this exercise of Mohr's circles is to find this feasible stress space that helps us visualize as to what will be the values of sigma n, sigma s for a given stress tensor sigma at a point P. So we will be deriving the equations, but I want to discuss what we'll get in the end and what it looks like. So these are the three circles called the Mohr circles, and the points at which they intersect the sigma n axis are basically the three principal stress values, sigma 1, sigma 2 and sigma 3. So in this case, we have numbered sigma 1, 2 and 3 so that sigma 1 is the largest eigenvalue of sigma or the principal stress value, and then sigma 3 is the smallest principal stress value for the stress tensor sigma through a point P. And when we identify the feasible stress space, that basically comes out to be this region between the circles. So this green region, which is the shaded region, is called the feasible stress space or the feasible stress region. So now from this visualization, we can very easily identify the maximum value of sigma n, because if you look at the feasible stress region, which is the green shaded region, you can see that this point is the maximum value for sigma n, so that's sigma n max. And then to find the minimum sigma n, you have this leftmost point. So this point is sigma n minimum, and to find the maximum shear stress, that is nothing but this top point here, which corresponds to sigma s. And as I said earlier, the minimum value of sigma s, which is just the negative value down below, does not have any significance. So magnitude wise, the minimum value of sigma s is simply 0, as we can see from this figure. And this minimum sigma s corresponds to the situation where we have sigma n max, sigma n min, or the intersection of the circles with the sigma n axis. And we can also quantify these values. So sigma n max is the largest eigenvalue, which is sigma 1. Sigma n min is the smallest eigenvalue, which is sigma 3. And if you look at the radius of the largest circle, which is actually sigma s max, which is equal to sigma 1 minus sigma 3 upon 2. And sigma s min, as I just mentioned, is simply 0, because we are only interested in the magnitude of shear stress in this case. So you can see that using these Mohr's circles in the stress plane, we can very easily visualize the feasible stress space and the stress maxima. So our goal now is to obtain the equations of these circles and the corresponding feasible stress space on the stress plane. So let's do that now. So just like we did in the method of Lagrange multipliers, we will be working in the principal coordinate system or the principal axis, because mathematically speaking, the work becomes very comfortable because the stress tensor takes a special form, that is a diagonal matrix. So the stress tensor sigma, it transforms to a sigma star in our starred coordinate system, that is the principal coordinate system. So basically sigma star takes this form, which is a diagonal matrix representation with the diagonal terms being the principal stress values sigma 1, sigma 2 and sigma 3. Again, as I said, that we have marked these sigma 1, sigma 2 and sigma 3 in such a way that sigma 1 is the largest principal stress value and sigma 3 is the smallest principal stress value. So in this principal coordinate system, we'll write sigma n first. Now sigma n is a normal component of the traction vector Tn hat as shown in the figure. So the traction vector using the Cauchy stress principle gets written as sigma ji nj, and then when you dot it with a normal, you get an ni. And you know that since sigma star, or we'll call it sigma now because we are working in the principal coordinate system, our sigma is diagonal. So this becomes sigma I times delta ji, So that's your stress tensor sigma. And then you have Ni times Nj. We apply the substitution property of delta that gives us sigma I Ni, which when expanded using the summation convention, remember these are the indices which are used for summation, and this is just an index that tags along in the summation. So this becomes equal to sigma 1 times n1 squared plus sigma 2 times n2 squared plus sigma 3 times n3 squared. This is our expression for sigma n in terms of the principal stress values and the three normal components. So we will mark this equation as 1 because we'll be needing this for our derivation. So please remember that in this case, ni's, which are the three components of the normal, are the variables, because we're trying to find the maximum and minimum values of sigma n and sigma s as a function of ni's. So ni's are the independent coordinates in this optimization exercise, like we discussed in the method for Lagrange multiplier in the last class. Next, we'll try to figure out sigma s. Now we know that sigma n squared plus sigma s squared is simply the square of the magnitude of the traction vector, which is T n hat I times Ti n hat. So I'll expand this using the Cauchy stress formula. This becomes sigma Ji and j times sigma Pi and P. I'm using a different index J and P because they're repeated indices and they cannot appear more than twice in this mathematical term. Now we substitute the diagonal form of sigma. So this becomes sigma I times delta Ji times Nj times sigma I times delta Pi times Np. We'll apply the substitution property of deltas and simplify this. So this becomes sigma I squared times Ni. Now again, summation happens over these indices and this index just tags along. So let's expand this. This becomes sigma 1 squared n1 squared plus sigma 2 squared n2 squared plus sigma 3 squared n3 squared. So this is our sigma n squared plus sigma s squared. And this equation we'll number as 2 because we'll be needing this as well. Finally, we have the condition that n hat is a unit normal. So we can write n1 squared plus n2 squared plus n3 squared equals 1, and that becomes equation number 3. So we can see that the variables in these equations are n1 squared, n2 squared and n3 squared. We already know sigma. Sigma is given to us. So sigma 1, sigma 2 and sigma 3 are known values, and sigma n and sigma s depend on n1 squared, n2 squared and n3 squared. So we have three unknowns, n1 squared, n2 squared and n3 squared. So we can write these in terms of sigma n, sigma s and the three principal stress values. So when you solve this, and I'll leave it to you to solve this system of linear equations, you get the equations for n1 squared, which can be expressed as follows. So I'll number this equation as A, and then we can see the expressions for n2 squared and n3 squared as follows. So let me remind you what we are doing. We're trying to find sigma n comma sigma s pairs for all possible n hat values. Because we have infinite choices for n hats, so the sigma n comma sigma s points when plotted on the stress plane will give us a feasible stress region. So we're trying to find the locus of all these points. So we're trying to find the feasible stress region. And for that, we'll be using an analysis-based approach. So let us look at equation number A. So in this equation number A, we see that sigma 1 minus sigma 2 is a positive quantity because we had chosen sigma 1, 2, 3 in such a way that 1 was the largest principal stress value, and this is also positive. So the denominator in this expression A is a positive quantity, and n1 squared is also positive. It's a squared of some number. So what that means is that this quantity, which is the numerator of A, is a positive quantity. Similarly, let's look at equation B. N2 squared is positive, and then sigma 2 minus sigma 3 is positive, but sigma 2 minus sigma 1 is negative because sigma 1 is greater than sigma 2. So this gives us a negative denominator. So that means the numerator of equation B is negative. So I'll write the condition for equation A, that is the numerator of the equation was positive, which is basically saying that sigma n minus sigma 2 times sigma n minus sigma 3 plus sigma s squared is greater than equal to 0. And this equation can be rearranged, which gives us the following equation, that sigma n minus a half of sigma 2 plus sigma 3, this whole value is squared, plus a sigma s squared is greater than equal to half of sigma 2 minus sigma 3, and this whole is squared as well. And this equation we'll call A1 because this is obtained from equation A. We'll also write the equations corresponding to equations B and C. So these are the three equations, which is equation A1, B1 and C1. Now we can see that equation A1 looks like the equation of a circle. Rather, it is a region which is outside a circle. So in the stress plane with the x-axis along sigma n and the y-axis along sigma s, this is sigma n minus sigma naught square, this is sigma s minus 0 squared, and this is some r squared. And because we have a greater than equal to sign here, that means that this is the region which contains the circle and all the region outside this circle. Similarly, for equation B1, we have a less than equal to sign here. So that's some region inside some circle. And for equation C1, we have a greater than equal to sign here. So that is some region outside some circle. So let us plot this region which agrees with all these three equations. So for equation A1, we can see that the center of this circle is the point sigma 2 plus sigma 3 by 2 on the x-axis or the sigma n axis and 0 on the sigma s axis. So let's plot this point. So sigma 2 plus sigma 3 by 2 is some point in the center here, and the radius is sigma 2 minus sigma 3 by 2, which is simply that we have this circle. Now let's look at equation B1, which has the center coordinates as sigma 1 plus sigma 3 by 2 comma 0. So 1 plus 3 by 2 is basically the center here, and if I draw the circle with the radius as 1 minus 3 by 2, that gives us the circle like this. And the third one is a circle which is tangent to these two, which is the red one. So these are the three Mohr circles. Now also, we are interested in the feasible stress region. So the feasible stress region, if you look at equation A1, is outside the green circle. From equation B1, it is inside the blue circle. And from equation C1, it is outside the red circle. So all the region which is inside the blue one and outside green and red one is this shaded region. And this shaded region is called the feasible stress region. So we have successfully found out the equations of the Mohr circles and the feasible stress region. So this completes our exercise in using the analysis technique for finding the feasible stress region. And now with this knowledge of the feasible stress region, we can now find out the stress maxima. So this point here corresponds to sigma n max. This point here corresponds to sigma n min. And this point here corresponds to sigma s max. I'll write the values for these stress maxima as well. So sigma n max is sigma 1, as we can see from the figure. Sigma n min is sigma 3. And sigma s max, that is the maximum shear stress, is simply sigma 1 minus sigma 3 upon 2, because we're only interested in the magnitude of shear stress. Now please note that the principal stress values can be negative as well. So I've shown that situation here, where sigma 3 in this case is a negative value. In fact, in these circles, when identifying the feasible stress region, we are satisfied with only the upper region, because as we said that sigma s min has no significance in terms of the negative values. So we can simply get rid of the region under the sigma n axis. And typically you will notice that Mohr's circles, or the feasible stress region, is drawn as only the region above the normal axis. So this is called the stress plane. And correspondingly, we also have a physical plane which is our O x1 star, x2 star and x3 star axis. Actually, Mohr's circles have much more information than simply giving us the stress maxima. For a given normal n hat in the physical plane, we can find out the corresponding sigma n comma sigma s point in the stress plane. So if my cutting plane normal was along x1 star axis, then I know that it will give me a situation where I'll have a purely normal stress. So if I was to write the traction vector, the traction vector corresponding to this normal will be sigma 1 times n hat 1. So this is n hat 1 because this is along x1 star direction. And on the stress plane, this would be corresponding to this point here. So this normal corresponds to this point. Similarly, if I was to have an N2 hat like this will correspond to the point here on the stress plane, which corresponds to sigma 2, and that's a purely normal stress situation. And if I was to have a normal along the third eigen direction, which is N3 hat, that will give me this point here on the stress plane. So we can start to see that different normals in the physical plane will give us different points in the stress plane. I've taken these special situations where the normals are aligning with the principal directions. So that gives us points on the sigma n axis. But if I was to take some general normal, let's say like this, and we call it some general n hat, that would correspond to some general point here in the stress plane region, because this point will have both a shear stress and a normal stress. Now we don't need to rotate our normal in the complete 360 degrees around the point O to generate the feasible stress region. In fact, we can only work in the first octant in this physical plane. So if I take points A, B, and C and draw the first octant of a sphere, you have to imagine this. Imagine a sphere. Since our sigma n and sigma s both are functions of n1 squared, n2 squared, and n3 squared, as we saw in the equations. So the first octant is enough, because in the first octant, my n1, n2, and n3 components are all positive. If you go to some other octant, you'll simply see that the signs of n1, n2, and n3 will change, but that will not give us any new point in the stress plane. So I can summarize that the first octant in the physical plane results in the complete feasible stress region in the stress plane. So a general normal will be shown like this, and this normal will correspond to some point in the stress plane, which is shown here. Now let's look at points A, B, and C. So the point A on the physical plane, as I've shown, let me change its color to the red color, corresponds to the red point here on the stress plane. The point B corresponds to the green point. So this is point B in the physical plane, and this is point B in the stress plane. And let's call the Mohr circle, which is a circle with the ends as sigma 1 and sigma 2 values on the stress plane, as the circle C1. So I'll label this as C1. So if I move from point A to point B in the physical plane, that is, if I move like this, so moving from point A to point B basically means that my normal is rotating from the one end at point A to one end at point B. So you basically have normals which are like this. So for all these three different situations, you will end up moving along the circle C1 like this in the stress plane. Similarly, if I talk about moving from point B to point C in the physical plane, that results in the movement from point sigma 2, that's the green one, to the blue one in the stress plane. So let's call this C2 and this is C3. And with the same logic, if I move from point C to point A in the physical plane, which is like this, that results in the movement from sigma 3 to sigma 1 in the stress plane. So what we have noted is that a 90-degree rotation in physical plane results in a 180-degree rotation in the stress plane. So this is an interesting idea that allows us to locate points in the stress plane given some location on the physical plane. Now if my normal was arbitrary, that is, if it had some location like it has here in n hat in the physical plane, where it intersects the octant in a point Q here, then that point Q will be some general point small q in the stress plane. Now doing that exercise is an exercise in pure geometry, and that exercise takes us, given a normal n hat for a given state of stress sigma, it allows us to locate sigma n comma sigma s values on the stress plane, that is to find the sigma n comma sigma s for a given normal. So it is much more comfortable working analytically, that is getting sigma n and sigma s values from sigma and n hat using the equations that we had just written in this lecture above. So this brings us to the end of this lecture on Mohr circles. Mohr circles are used extensively in continuum mechanics for visualizations. So one must understand how they are obtained, what they mean, and what they depict. And we have successfully done that in this lecture. So we will be using these visual representations to understand different states of stress. For instance, in the next lecture, we will talk about plane stresses, and again we'll touch upon the visual representation of that situation using Mohr's circles. So before we end this lecture, here is a concept check problem. So in the inverse problem, if sigma n and sigma s values are given, that is the pair sigma normal comma sigma shear is given to us on the stress plane, how do you find out the corresponding cutting plane normal vector n hat in the physical plane? So this can be answered using the equations that we developed in the beginning of this lecture. So thank you very much, and I will see you in the next lecture.